Hello and welcome back to High Peak Education. I would like to record a lecture video about rotational dynamics. In particular, I'd like to start focusing on rotational kinetic energy and then also rotational inertia, which is the rotational equivalent of mass. This is the later slides of a previous video where we studied rotational kinematics, tangential acceleration, centripetal acceleration, and the definitions of rotating variables, including things like period. So, let's begin with rotational kinetic energy. So, rotational kinetic energy is defined as the following. This rotating object has an axis mounted on it, has no translational motion. In other words, its axis here does not move horizontally. Its center of mass also doesn't really displace. But it is in motion, so it must have kinetic energy. So, in order to have kinetic energy that we haven't defined yet, we should use what we know about kinetic energy. Now, kinetic energy is 1/2 mv squared. But let's put mi and vi and subscripts of I and add up all these little point masses. Now, because it's a large extended object, there's sort of an infinite number, but not an infinite number, just a very large number of very small point masses on this extended object. Okay? But each of them, we know v is like omega times r. But notice that the r is going to be different depending upon the object. So there's going to be an ri associated with each object. But the omega is going to be the same for each object. So the omega squared is just going to be a constant for all objects. So with the tangential velocity definition, we'll derive the rotational kinetic energy. Notice that you're going to have omega squared here, but then you'll have mr squared. So we'll define this new quantity called capital I. And capital I is the so-called rotational inertia, sometimes known as the moment of inertia. So rotational kinetic energy is 1/2 I omega squared. Notice that instead of 1/2 mv squared for linear, it's 1/2 I. Rotational inertia is like rotational mass times angular velocity squared. So if a rotational axis is moving, say linearly, we would need to consider the translational kinetic energy too. That we'll see when we actually get to rolling objects. So let's study this rotational inertia in greater detail. What is it? Think of it as the rotational mass. In other words, the equivalent of inertia for linear. Now we have rotational inertia. It's the measure of the tendency of an object that is rotating to resist a change in rotation. That's why it's called the moment of inertia. So notice that it's the rotational equivalent of mass. But notice that the rotational inertia for a point mass, a single point mass like we saw in the previous slide, made up of a lot of small point masses, is mr squared. Mass of that small point mass times its radial location from some axis of rotation squared. Notice the units. They'll be kilograms times meters squared. Unlike mass in linear motion, with Newton's first law of motion, which was inertia, rotational inertia strongly depends upon the radius. In other words, when it comes to rotation, inertia and tendency of an object to stay in the rotational state that it's in does not only depend upon the mass, but it depends upon how the mass is distributed with radius. So generally, are objects harder or easier to rotate as they move from the rotation axis? Why? So they should be more difficult. You can hopefully prove this to yourself if you have just a small writing implement nearby. If you try to rotate it near the center, the radius to the mass is pretty small. But if you try to rotate it out near the end, it's much harder to rotate. And that's because it has a much larger radius, even though it's the same object. So, the more mass is further away from the axis of rotation, the harder it is to rotate. Okay, so let us talk about rotational inertia with respect to shapes and axes. Part of the reason rotational inertia is so important is because many times we will have solid body rotation. We will have extended large objects made up of many point masses in a particular shape that we will want to rotate around a specific axis of interest. Now, it turns out that many extended objects are possible, and we have to note the location of the axis of rotation in each case. And for each derived formula, note how the mass is distributed toward or away from the axis of rotation. Now, by the way, rotational inertia for an extended object can actually be calculated using calculus. It turns out the formula is something like the integral of r squared dm, because notice that if we had a single point mass, this would just be mr squared. But notice that if you've got a bunch of little mass elements all the way distributed throughout an object, that's like dm. And you add up all those dm's over some extended object, you should have the total rotational inertia. Now, by the way, a lot of times in many of these situations we assume constant density, so we replace dm with rho dv. That is mass density times volume differential. It's usually easier to integrate over a volume than it is over mass directly. Now, some of these calculations are beyond the scope of what many professors expect their students to do, but many textbooks can show you how to calculate these formulas. Okay? So notice, what if you have a hoop? In other words, all the mass is on the outer ring. And by the way, this ring is very thin. Well, it's still mr squared, just like a pendulum whirled around a string, vertically, because all the mass is on the outside. So it's still almost like a point mass, but just all at the outside, so it's mr squared. But notice a solid cylinder. A solid cylinder is going to be 1/2 mr squared, because it still has mass along the outside, if rotated about its center, but it also has mass on the interior. And since it has mass on the interior, it's going to have a smaller rotational inertia, namely 1/2 mr squared. How about a solid sphere rotated about its center of mass? Well, it's got a bunch of mass in the center, because it's not just along the central axis, but for the sphere, all the mass is near that center of mass point, or not all of it, but at least a bunch of it. So there's less mass on the outside than there is for a solid cylinder, so it ends up being 2/5 mr squared. Notice that this is like 100% mr squared, this is like 50% mr squared, this is like 40% mr squared. Notice that as the mass is getting closer to the center, the rotational inertia is getting less. So objects with their mass closer to the center are easier to rotate. With mass further from the center, harder to rotate. Now you may ask, what's the formula for these shapes? And I have no idea, because these aren't really nice shapes. But in general, as mass moves further away from the axis of rotation, the difficulty to rotate, in other words, the rotational inertia, gets more substantial, gets more difficult to rotate. So let's talk more about rotational or moment of inertia. For a collection of point masses, you sum all the mr squareds. So I is mi/ri squared, sum over all I, and I is an index. The moment of inertia for a continuous object is the sum of how all the mass elements are distributed with a radius. Okay? And that's going to be I equals r squared dm. I already alluded to this, that if there's some mass distribution where the mass is more massive and less massive in certain places, you can still find this rotational inertia, but you'll have to integrate the whole thing. Now, in many cases, suppose we know the mass density. Well, if we know the mass density, that's mass divided by volume. So mass density times volume should be that differential of mass. So rho, especially if it's a constant volume, times dV should replace dm, and r squared is still there. So notice this is in general much easier to integrate over if you understand something about the mass density. Now look at this table of moments of inertia for extended shapes. In fact, most of you taking a physics class right now should have a textbook or some sort of reliable online resource, and you should be able to find a table that's very similar to this. Now, by the way, notice that these tables are also available online or in engineering manuals and so on, but notice that these tables are such that people don't memorize these things in general. All of these equations can be derived basically using calculus principles like so or like so, but somebody has already worked out the answer for you. So I would not recommend work out the mathematics yourself, just use the table. And by the way, these are not formulas that people tend to memorize, so hopefully if you take an exam, there should be a table like this provided for you on an exam, even if there's a bunch of formulas you must know. So as I already mentioned the hoop, or the very thin cylindrical shell, which is mr squared. I already mentioned the disk, or what we call the solid cylinder, as 1/2 mr squared. I already mentioned the solid sphere of 2/5 mr squared. Notice that all of these rotational inertias are about their center of mass. Now, what if things are a little different? Notice, look at a hollow cylinder. It has an inner and outer radius that's 1/2 m r1 squared plus r2 squared. Look at a plane. A plane depends upon its width and length and its mass, and it has a 1/12 in there. Notice a long thin rod about the center, a lot like a plane, has a 1/12, but it's ml squared. And look at this rod if you rotate around the edge or the through the end of the rod. It's larger. It's 1/3 ml squared. And look at a thin spherical shell. So a thin spherical shell might be something like maybe an iron basketball. So you can imagine a basketball is kind of a thin spherical shell, but if the outside was sort of very massive, it would have a rotational inertia of 2/3 mr squared. Notice that is larger than the solid sphere of 2/5 mr squared, because again, more of the mass is on the outer edge. So I will perform this calculation as well in a later video, and I'll show how rotational kinetic energy and linear kinetic energy are equivalent if you understand the linear to rotational conversions. Now, how about the moment of inertia of a continuous object and a point mass example? If a point mass, mass m, is placed on the edge of a solid cylinder, what is the new moment of inertia? So I will calculate that in a later video as well, but I'll tell you it's relatively straightforward. Okay? But in order to find, say, the rotational inertia of this cylinder, you'll have to use calculus. But again, you should get the answer that you expect, which is this 1/2 mr squared. And here's another example where we have to use conservation of energy. In other words, in the absence of non-conservative forces, mechanical energy is conserved. Now notice, mechanical energy can include rotational kinetic energy, which we have not seen thus far. So I will show this example again in a later lecture video. So thank you very much for your attention. Please smash that like button if you enjoy this content, and please subscribe to the channel to grow the channel. Please spread this around your social network, and I look forward to looking at your comments, and I want to thank you for watching High Peak Education. I will see you in the next video.